Okay, let's start exploring constraints and the rig VOP a lot more in depth now. The rig attribute VOP a lot more in depth. And we'll also talk about local and world transform data for these points. So let's start by setting up a new kind of system where we will explore the packed geo real quick. Let's just put down a point with an add sob, and we'll turn it into a joint with our rig doctor. Initialize transforms. We'll put down a rubber toy. This will be our geometry to explore transforms and constraints. And we'll do a capture packed geometry real quick. Get some errors, which is fine. We'll put in our rubber toy as our skin geometry, and our rig doctor, which is now our joint, our skeleton, as our skeleton. We'll add a new skinning. We'll select that joint. The capture pack geo seems to be a little bit funky right now, which is fine. It still works in a way. Put down our bone deform, and we can hook up all of our joint chains, and we can even put a rig pose real quick in here for our deform path. We're getting a little bit of an error here for our capture because of that weirdness we were experiencing with the pack geometry. Let's select pack inputs because we didn't have a pack geometry, and now we should be able to have a good solve there. There we go. And now we can control that rubber toy with our joint there. Perfect. So let's start to explore constraints simply by putting down a different joint here. We'll put down a new joint that is a little bit behind our first joint, just back there. And we'll also turn it into a joint with our rig doctor. And here I'm just going to put down a null just to separate out some things. And we'll call these our constrainers. Now let's put down a rig VOP. And we'll input our, I'm actually going to just put our rig pose over here. And we'll just put our deformer path through our VOP and our constrainers into our second input. Now let's start to explore that section of getting and setting point transforms that we had started on when we first opened our VOP the first time when we started to explore kinematics. So we're just clicking on these points interactively in our VOP, and when we click on them, if there's multiple for that point, such as our first input, it gives us our input point and our output point. As we can see, when we drag on the second option, we get a get transform. So that's our input point, and if we drag on our second input, we get a set transform. That's our output point. And we're going to grab our point 0 from our second input, and we can grab our point 0 from our first input as well. To make this cleaner, we could also have named our joints other than using the rig doctor. So I'm going to go ahead and fix that real quick. I'm going to name, I'm going to not initialize missing names here. I'm going to name our one joint constrain joint, just so we have an easier time down the line here. We'll now need to fix our get point transform for our second endpoint, because we no longer have that naming of point 0. Okay, so Houdini just crashed on me, and sometimes that just happens. I've noticed it happening a lot with Houdini 19 when we're interactively selecting points in the viewport through any means with just KinFX pipelines in general. So just be careful with that. Make sure you save your work. Anyhow, back to our point transform. As we'll notice, we now have a different name, so our point 0 isn't going to work for grabbing that point from our second input anymore. We could just replace it, or I could just drag it on and it comes through with our name. So a few things that we can explore is simply these X forms and local X forms for our from our point transforms themselves. So when we put in our X form just directly into our set point transform, as such, we'll notice that our rubber toy gets snapped back to our constrainer point. This is just matching our joint from our main chain, our rubber toy chain, directly to our joint of our constrain chain in a world space fully. So there's no difference between the joints effectively after the fact of our constrain exploration of our rig bop here. So this would be similar to, in Maya, applying a parent constraint without maintaining offset. Alright, let's reset that point back to 0. Don't need this guy anymore. So that's what happens if we hook up our X form, just our world space X form. If we hook up our local X form, we kind of get a similar situation. Our spaces collide again because the local X form for our 0, if we just put down, oops, reorganized our thing there. If we put down a skeleton here, and well, I'm not sure what I did to the viewport there. There we go. To explain and explore local transforms further, let's put down a few joints with the skeleton node. Just 2. And we'll go into modify real quick, and we can start to select these different joints. When we pull up that P menu from earlier, we can see our local transform data and our regular transform data. We can see that the child of our parent, and we'll just, for simplicity's sake, put our parent joint at 0, so that our local transform is at 0 as well. We can see that our child point has local transform data, and our parent point, it could as well, but that the local transform data of our parent point matches exactly with the world transform data, whereas it's not so with our child point. If we set our child's local transform data to 0, we'll see that it matches our point, our parent point exactly. There's no difference between our parent point and our child point. We can also notice that our, if we turn on orientation real quick, joint axes, our Z defaultly points down the chain towards our child point for our skeletons. We can move that around, and it was based on our initial creation of that joint. And we can see that default, the Z-axis points towards its parent. So our skeleton creation node tries to orient our joints in a logical way that we might want. As we change around the local transform data, just in this node here, we'll do it much smaller, we can see that it is in correlation to that orientation. As we move this back and forth in the Z axis, it kind of follows along with our orientation, but seemingly as if it's going with the x-axis instead of our z-axis. We can see the same effect here with moving our, or sorry, I was mistaken, the XYZ, my bad. We are moving exactly in correlation with that orientation of our parent data. And if we move in world space, we're just moving in world space logically back and forth, left and right with that world space. Just as such. So if we were to hook in a new skeleton real quick, and we were to grab those joints from our constraints, which when we plug in a skeleton into a skeleton node, all it does is kind of copies a template of it. As we can see, we now have that named skeleton, and even though we severed the connection, it's still there. If we pull up our point data there, our local transform is exactly the same as our world transform. And if we were to see the skeleton of our main chain here, when we do so, since this is our parent joint for both chains, we're effectively not changing much between hooking up our local X form and our world X form. Those are the kind of important things to know for X form and local X form and constraints for the time being. We'll explore this a lot as we enter in more complex solutions to our rigging problems. But for now, we'll move on to an actual constraint node, which if we just look up constraint, we have only two constraints in KineFX. We have a parent constraint and a look at constraint. Our parent constraint allows us to do a similar thing to inputting our X form directly. As we can see there, we snapped directly. However, if we wanted an offset, we could click this update offset. So I initially set up this constraint wrong really quick. I forgot that there was a second input we need. Obviously, a parent constraint needs a new parent, which I totally forgot to hook up, just in light of connecting things directly. We actually want to take our X form of our point that we want to constrain instead of our constrainer point, and our constrainer point becomes our new parent. And now when we collect the update offset, we can see that that offset is updated instead of just snapping right to it. Of course, if we don't want that offset, we can clear the offset and we have that exact same kind of 1-to-1 ratio that we had just been doing without the parent constraint. So let's use that update offset. And now when we control our constrained point, we can see that that is exactly maintaining its distance from our point initially, as we can see here. Perfect. Now, there is another way to approach this that perhaps maybe we don't want to use a constraint because maybe our offset is changing before we can update it, and we can't update it every frame or so. We'll encounter this issue when we try and put a weapon into our character's hand later in the course. How do we solve if we don't know where our constrained object is going to be? For instance, our constrained object for a gun would be its hand. If we're moving the hand of our character, how do we always update that offset from our weapon, our rubber toy? Well, we don't have to use this parent constraint necessarily. There's a workaround that we can do that allows us to be able to change however often we want to, always be updating this, and then go into constraining our object later. Let me just reset this real quick. The way we're going to do that is not with the VOP at all, actually. We're going to use a parent node. So if we want to be able to move this joint, say over to here, and then we want it to be able to constrain this so that later on down the chain, when we start moving it, as so, up here we want to be able to position our constrainer joint. Then somewhere in between these two things, we then want this to move this joint. Well, we can put in a merge node up here, and we can merge our two chains so that now we have both joints in one place. We can put down a parent node, and we can say this should become our parent to that. And we can see immediately that once we start to move this constrained object and we look at that parent, we can see that that's updated however we need it to be. Now when we move this parent over into our new rig pose down the line, when we move our parent joint, when we move that parent joint, we're moving our point 0 as well. To get it back into the chain, we need that skeleton blend node. We're just going to put it after this VOP here that we've been skipping. And we'll do a world space change. And we want to make sure we're changing towards our right side there. Perfect. I'm actually going to just, for clarity reasons, skip the VOP entirely. We're taking our pre-chain, merging it with our control chain, setting up a parent system, which is, I mean, it's called a parent constraint, so it's very similar kind of thought process. But we're just setting up a parent in total. And then we can repose wherever that parent is before we parent, and then change how we want to move it. And then we blend that joint back in, and we can see a similar result. But like I said, we can always move where our parent joint is initially, and then have it reset up as such, which is helpful for when we are, like I said, trying to position a weapon at a certain point, but that point keeps moving, which would mean we'd always have to keep updating this offset every frame, which isn't really viable. So there's this method to kind of creating a custom constraint as well. So that's been a good brief introduction into constraints. We'll explore it a lot more in depth as we need to approach these problems to solve. For now, we're going to hop back into our tube chain of things. So we've taken a look quickly at the parent constraint here, and we've talked about world space. Let's explore another constraint, that second constraint we saw when we looked up constraint, the look at constraint. When we put it down, we see that it's not too dissimilar from our parent constraint. It just has a few more options here, and we've got some different inputs. So firstly, we want that x form for our point that we want to manipulate, which is our point 0 again, and our look at point, which is going to be our constraint object. And another very helpful input, depending on what we're doing, is a lookup, which can be a point above either our constraint object or right above our other point, that can help us maintain a good orientation for our constraint. And we'll see here in a second what I mean, I bet, when I plug this in. So currently our axes are kind of lined up in a way that's well with our rubber toy, aiming down the z-axis with y up, which is good. When we move this around, similar to how we had to reorient some of our axes with our IK solvers, we have to do so with our aim constraint as well. And right now the aim constraint is working very well, and as we can see here, it's a pretty simple concept. The point that we are constraining does its best to orient the axis that we determined as our look at axis as best towards our point as possible that we are constrained to. Very helpful. Sometimes to keep a better orientation, or if we need a better orientation, we can off-split our main chain here. So I'm just going to grab a rig pose here to split off our main chain and put it into our third chain here. And we can take this rig pose, and I'm going to show us how we can just use this up chain to flip our rubber toy around here. I'm going to take that point that we just produced, our third input point, and I'm going to put that into our look up. So now our y-axis is up, which is good, and it'll do its best to consider wherever this point is as y up. So it'll try and orient our y-axis towards this point, and it'll try and aim our z-axis towards our aim point. This is useful for if our axis isn't oriented properly. We got lucky with how it was oriented, but say our rubber toy was defaultly upside down just because that's how it interpreted, we can use this point to help us orient our rubber toy how is needed, or our joint how is needed for our cases. It's very helpful, and that's kind of a quick breakdown of our look at constraint. I rarely use the offset for the look at, but you can create an offset just like we could for the parent constraint. And the blend option is available to us by default as well, which just lets us blend between no constraint and the constraint completely on as well. We can see that the blend parameter is available on our parent constraint as well, and we can do so with that and even promote it if we want to. So we're going to explore one more cool kind of constraint before moving on, which is a constraint that allows us to move joints along a path. So here I've created a curve just by placing things down on in the scene, and I'm going to put it into a rig doctor node to initialize some name transforms, or sorry, some names. And we're going to put that into our second input for our VOP instead of our constraint points. When we dive in, we're going to want to make sure we have our set point transform to our point 0, and we're going to create a transform from path. And we'll give it a second to think. There we go. So we have a transform from path, and we have it in our second input. And instead of inputting our constraint data, we're just going to input our out form from our curve into our x form for our point. And we can see now that we get that that snap to our curve already. And if we click on our transform from path, we can edit these parameters a bit to see it move along the path if we want to. And if we wanted to orient towards our path as well, we can change our look at offset to be just slightly more than 0. What the look at offset is it points towards a position on the curve. As we can see, the offset is now at 0.3ish. He's looking at around this point on the curve, and as we go along the curve, he'll look that far ahead on the curve as well. So a minimal offset will mean he's looking right in front of him as we go along the curve. Perfect. And of course you can promote these parameters if you want to see them on the SOP level, or whatever you would like to do with that.